Now we're going to talk about vertical stretches and compressions. So this graph here shows an example of vertical stretching and compressing. So this blue line here is in the middle there. That is the original function. Then if we multiply it by 2, you get the light blue line. If someone's going to correct me on the color, I'm sure. So that's a stretch. It's stretched by a factor of 2 because that's its coefficient. Whereas this orangish line is it's kind of squished down and it's compressed by a factor of 0.5. So all those values are half as much. So the vertical stretch, all those values are twice as much as the f of x values. So vertical stretches and compressions, given a function f of x, a new function g of x equals a times f of x, where a is a constant, is a vertical stretch or vertical compression of the function f of x. If a is greater than 1, then the graph will be stretched by a factor of a. If a is between 0 and 1, the graph is compressed by a factor of a. And if a is less than 0, the graph is either stretched or compressed and is also reflected about the x-axis. So it kind of ties into the last video's discussion about reflected graphs. How to graph a function with a vertical stretch or compression. Identify the value a, multiply all range values, that's the output values, by a. If a is greater than 1, the graph is stretched by a factor of a. If it's between 0 and 1, it's compressed. And if it's less than 0, as I said before, it's either stretched or compressed and also reflected about the x-axis. Okay, so we're going to do example 10 here. The function p of t models the population of fruit flies. A scientist is comparing this population to another population, q, whose growth follows the same pattern but is twice as large. Sketch the graph of this population. So we're looking at a stretch here, so everything's going to be twice as much. So I'm going to change colors to that. So 1 will actually go up to 2. This 3, 3 go up to 3, 6. 6, 2 become 6, 4. And then 7, 0 times 2 is still 0. So it's going to curve up like so, come down here, and then come down to the, it's not a very good line, but yeah, I think you get the idea. It comes down there. Boy, I can't draw a straight line today. You're arguing, but you haven't drawn a straight line yet at all. Okay, that's a little better. Okay, moving on. I do want to get rid of this because it'll show up in the filled in notes. How to create a tabular form of a vertical stretch or compression of a function. Determine a value of a and multiply all the output values by a. I don't know if you can hear, I don't know if the microphone's picking up my dog's panting. I just got back from a walk. Okay, so here we have the values. What we're really going to focus on is this f of x row because we're looking at 3/4 of these output values. So 3/4 of 12, it's going to be 9. 3/4 of 16, it's going to be 12. 3/4 of 20, it's going to be 15. And 3/4 of 0, that's a 4 there, it's going to be 0. Okay, now example 12. The graph is a transformation of f of x equals x cubed. To relate this function, this new function g of x, to f of x, and then find a formula for g of x. So our f of x, would have gone through 0, 0, but it would have gone through 1, 1. And then it would have gone through 2, 8. So it'd be way up there. I can't even, maybe it's obviously on the graph, it's way up there. It would have gone through -1, -1. Would have gone through -2, -8, so way down there. So I think the real helpful part is this right there. So this g of 2 equals 2, where f of 2 would have been 8. So what is 8 divided by 2? It's 4. So the compression factor, because you can see it's obviously compressed since it's squished more than the original. Compression factor is 1/4. So it'd be f of x equals 1/4. No. Oops. That's a g. F is the original. G of x is 1/4 x cubed. That's it. Okay. Next video we'll talk about the horizontal stretches and compression.